Welcome to the course on Introduction to Electrical Engineering. Today we will discuss lecture 8. The topic is tangent response of first order circuit. The second part we discussed first part last time, and with the outline of today presentation is we will talk about first inside and real time or real life application, then singularity functions, then we will talk about the step response of RC circuits and step response of RL circuit, and we will go ahead with the some of the exercise and of course, with the numerical solved problems like followed by references. To start with, we will discuss with some insight and real life application where these you can call it the response of first order system is used or first order system are used. Typical examples are like a delay circuit. As you can see here, the time delay relay using I555 timers. In that we use the circuit, of course, RC circuit for the providing the delay. For with respective pins of this circuit like Then of course, there is a further delay relay. We use here typically the delay circuit in neon lights, use RC delay timer circuit for periodic on and off of the light, like you can see these lights which are quite popular in the typically in the market or for the some of the you can call it commercial buildings or the mall or other places, like for the purpose of decoration with the different shapes and different lighting arrangement like Then another is delay circuits for LED strip probe light, and with the delay it is going changing the colors of different parts of the display. Then another example is typically like a color changing neon LED light strip light, as you can see like how really it really gives the picture in sense. And then of course, you have a typically RL circuit related to the motor, which really we need the analysis for that. And then of course, we have a delay circuit in this, which example we have given of a neon lamp, and here is a typical RC delay timer used in the neon light for periodic tuning of on and off of light. So, in this circuit when we close the switch, of course, the capacitor gets charged, and once it charged to higher than typically a 70 volt, then certainly the neon lamp start glowing, and then we open the switch and then this capacitor gets discharged across the lamp, neon lamp. So, that is how the basic principal operation is used this RC circuit for the purpose of delay. Because it takes some time to you can call it like to turn on this neon lamp till it get the capacitor voltage up to 70 volt out of this when we are applying 110 volt like. So, the lamp will act an open circuit and not emit any light until the voltage across it exceeds a particular level, say 70 volt. When the voltage level is reached, the lamp fires, goes on, and the capacitor discharges through it. Well, the another example is typically photo flash unit, as you can see in the typically with the camera. So, digital camera flashlight utilize a RC circuit to create a short duration high current pulse to energize the flashlight. The another example of flashlight in the DSLR, CSC or compact cameras. In different camera we have a flashlight. So, basic concept of principle for having a flashlight is the same with the delay circuit like And then this example of what is the circuit here, you can just see typically the circuit for flashlight providing slow charge in position 1, which charges the capacitor, and on position 2 fast charging display on position 2, because this R1 is much lower, much higher than R2. So, it charges slowly, but discharges at very fast rate, because it is a R2 is quite small, that causes the typically the your photo flashlight to work in the manner with the delay. So, this is a typical, here you can say how the capacitor voltage slowly charging and fast typically going up, and then suddenly when you change the switch, then suddenly discharges, and how the current goes. In this case, initially you can say current is high typically for charging the capacitor, and then it goes to almost 0 when capacitor is almost fully charged, and but when you are really discharged through R2, the current goes to typically much higher value of I2, and then slowly the capacitor gets discharged again comes to 0. So, that is the basic concept how we use this concept of capacitor charging discharging in the photo flash unit like. Another example is a relay circuit, as you can see in the circuit here. So, it operated from DC either 5 volt, 12 volt or 24 volt delay timer relay and have a self locking delay for on off time switch like. Well, so that is typically the how the you can say the display unit and timing circuits are there. Then another relay circuits are relay coils is nothing but an RL circuit used to control the switching of another circuit, I mean through these kind of relay and the PCB which you see on the for energizing the relay coil also. Then this is the basic circuit how the relay circuit contact is there. Okay. So, that you can see in both the cases when it is closes then it makes electromagnet and it attracts the arm, and then when it goes out then it de-energizes and automatically the contact goes to normal position like. So, these are the basic principle how really these relay coil means relay circuit operates with the force of attraction of the electromagnet created by closing the switch and opening of the switch. And this is the basic principle, then when you close the switch it becomes electromagnet and it closes the switch like, and that is the circuit how it is really going to be in that way. Otherwise, till it is not energized the switch remain open. So, we call it like normally open or normally closed switch conditions used normally in contactor and relay, I mean, and their application or utilization for control of power flow in many of the circuit and including the automatic electromagnetic starters like, I mean, also the basic concept used there as well as even in used for energizing the circuit breaker or many control valves also with the help of this solenoid or kind of the relay energization with the electromagnets like. This is another example of automobile ignition circuit. I mean, you might have seen the spark plug which are used normally in most of the two wheelers or many of the circuits for the purpose of typically sparking and providing the ignition in the automobile engine of the your two wheelers like. So, the gasoline engine of an automobile requires that the fuel air mixture in each cylinder be ignited at proper time, I mean like, and this is achieved by means of a spark plug which essentially consists of a pair of electrodes separated by a small air gap as you can see here like also. And the basic concept is here, I mean initially this is a automobile ignition circuit where this when we close the circuit of course, the the current flows through the inductor because that circuit is open, and initially of course, the current builds up because of inductance, and when finally the current in this circuit is stabilized by the resistance only, and inductance does not take any drop because finally the current goes to steady state value. And when you really open the switch because of LDIT you have a large voltage because suddenly you are interrupting the current of this circuit. So, now there is no path of this inductance current from the source. So, now because of LDIT suddenly a large voltage comes across the spark plug and you have a spark over the air gap which causes the flash to appear, and that really utilized for igniting the automobile engine like or circuit like. So, ability of inductor to oppose the rapid change in current makes them useful for the arc or spark generation like. As you can see the total circuit, we have a battery, we have a lick switch which is the switch we have shown there, followed by the other accessories and the coil here, the inductance coil here which is responsible for representing this automobile ignition system like. So, now well these are the practical applications which we discuss it, but how we can analyze the performance, we use the concept of singularity functions, and singularity functions are the different function which we create the you can call it the kind of pulses of different nature that we will discuss here. So, singularity function also called switching functions are very useful in the circuit analysis and are used really in practice like to analyze the performance of various applications like. So, typically example they serve as a good approximation to the switching signal that arise in the circuit with switching operations, and a basic understanding of singularity functions help us to make sense of the response of first order circuit to a sudden application of an independent DC source or current source for these RC and RL circuit like. So, singularity functions are the functions that either are discontinuous or have a discontinuous derivatives like, and we define this the three most widely used singularity functions in the circuit analysis are the unit step, the unit impulse and the unit ramp functions like. And typically starting from the unit step function, the unit step function is 0 for the negative value of the time and 1 for positive value of time, as you can see here in the typically in the figure as a unit step function. So, it is 0 and at time t equal to 0 it comes as a 1, and in mathematical terms it can be explained u t, we define it equal to 0 if time is less than 0 and equal to 1 when time is greater than 0. It can be like a kind of periodic function or it can be like a continuous signal, but more important here is the only the unit step rise, like that is used for the purpose of energizing these circuits and like used for many applications of such nature like. Well, unit step can be delayed by a t0. So, in mathematics as you can see here, we are not really going at t equal to 0, we are just having this you can call it to ramp up or to step up at the t equal to t0, and mathematically it can be now defined as u t minus t0 equal to again 0 if t is less than t0 or 1 if t is greater than t0. Well, the unit steps can be advanced also by t0, as you can see from 0 period it can be advanced to minus t0, and this in mathematical terms it can be explained as u t plus t0 equal to 0 for t less than minus t0 and 1 for t greater than minus t0. Well, step function is used to represent or an abrupt change in the voltage or current, and like the changes that occurs in the circuit of control system and the digital computer. For example, the voltage like a V t equal to 0 for t less than t 0 and V equal to V 0 for t greater than t 0. It may be expressed in terms of unit step function as V t equal to V 0 u as a function of t minus t 0, as you can see the typical circuit here. If it is connected to, let us say, to here directly to the green here, and at t equal to 0 we connect to the switch here, then this circuit becomes in this manner. So, you have a typically you can express it the V 0 at u t, the voltage source V 0 u t and its equivalent circuit here can be represented in this manner, like how you can define the function as we were discussing earlier. For t less than 0 it is just closed here. So, you have a like 0 value of this function, and when you connect it to here at t greater than 0, then it becomes this circuit with which you have a the voltage applied suddenly equal to V, corresponding to the defining with the u t as a step function. A current source depends on the circuit. Sometimes we have a current source also, a current source I 0 u t is shown here. So, here also it can be a source can be shown as I 0 u t with the equivalent to as a current source here, independent current source, and it can be expressed in its equivalent circuit. That current source never can be kept typically open. So, you can call it is here connected to here initially to 0, and once it is connected to t equal to at this current from the current source, current flow to the your circuit for which you are interested to find out the response like. Well, so that is about the unit step function. We have another singularity function which we call it unit impulse function, and this unit impulse function delta t is known as a delta t is 0 everywhere except at t equal to 0, where it is undefined value. And the derivative of the unit step function u t is the unit impulse function delta t, which is written as delta t equal to d upon dt u t derivative of u t, and this will be defined as t equal to less than 0, it is 0, at t equal to 0 it will be undefined, and at t greater than 0 it will be again 0. So, this can be represented as a graphical form. You can say we have a at t equal to 0 we have a function as delta t, and this is called unit impulse function, and unit impulse function also known as the delta function, and is shown figure in this case as you have a typically the value only at t equal to 0. This also can be the unit impulse may be also regarded as an applied or resulting shock, and it may be visualized as a very short duration pulse of unit area, and this may be expressed mathematically as typically minus 0 minus to 0 plus delta t dt equal to 1, because it is only at the, you can call it at the time equal to 0. Like, and few examples of impulse functions are shown here in the figure. So, you can say there are 3 impulse functions. We have at t equal to minus 2, that is 5 delta t plus 2, because it is advanced by 2, and then we have a impulse function at t equal to 0, that is your 10 delta t, and then we have impulse function that is typically, you can call it at typically delayed by a 3 second. So, that minus 4 delta, because minus value at the t minus 3, that is typically you can call it delayed impulse function. So, on the graphical we can just show these 3 impulse functions, which are certainly either advanced or at the t equal to 0, or it is delayed by 3 seconds like. Well, there is a third, you can call it the singularity function, which also used to study the response of these system or circuit, and this is the typically integrating the unit step function results in the unit ramp function R t, and that R t can be defined as minus infinity to t u t dt, and it is also because integration of typically will be t into u t, and we can define this R t equal to 0 for t less than 0, and it will be t when t equal to greater than 0, because u t here itself will become for 1 for the you can call it t greater than 0. So, it will be like kind of a ramp function, and you can see the here how it look like a ramp function. So, unit ramp function is 0 for negative value of the time, and has a unit step function for value of t, which is you can see the here, and it becomes the 1 value at the time equal to 1 second like as you see here. So, this is third singularity function, which normally used for the analyzing the these your first order circuits like, and unit function can be also delayed by t 0 as you can see here, and the expression can be written r as a function of t minus t 0 equal to 0 for t less than t 0, and t minus t 0 greater than for the t greater than t 0, and you can see how it is graphically presented here. So, since it is delayed by t 0, after t 0 plus 1, it will become value 1 of this your unit ramp function. Well, this unit ramp function can be also advanced by t 0 minus t 0 as you can see here on this graph, and that can be written r t r as a function of t plus t 0 will be equal to 0 for t less than minus t 0, and will be t minus t 0 will be at the t greater than minus t 0, and you can see how it is there. So, after again minus t 0 plus 1, it will be the value 1 for this ramp rise function. So, it called typically a unit ramp function advanced by the time t 0. So, you can call it these 3 singularity function like impulse, step and ramp are related by differentiation as delta t equal to du upon dt, and ut will be ut is dr upon drt upon dt, or by integration as ut will be as you take a typically a integration here of this. So, it will be minus delta minus infinity to t delta t dt, and r t will be of course, here will be a minus infinity to t as a u t dt from these 2 derivatives. So, they can be represented either in terms as a derivative with the other function, or it can be like a represented as a integration like. Well, we can see the step response of an RC circuit. This is typically the concept where we can say when the DC source is suddenly applied to the voltage or current can be modeled as a step function known as a step response. So, step response of a circuit is its behavior when the excitation is a step function, which may be a voltage or the current depends on the voltage source or current source like. So, as you can see here, like we have a DC voltage source, independent DC voltage source with the resistance and capacitance, and we have a capacitance may be having a charge on it in terms of voltage V, and when we close this switch at t equal to 0, then circuit becomes in this fashion finally, and depends on the value the how it is goes, and this capacitor may be charged to equal function. So, that is something how. So, we can find out the of course, the response from that, how we can analyze this circuit. So, analysis consider the RC circuit in that figure, which can be replaced by a circuit in figure B, where Vs is the constant DC voltage source, and select the capacitor voltage as the circuit response to be determined. Assume an initial voltage V0 on the capacitor, although this is not necessary for the step response, and since capacitor voltage can not change instantaneously, so that your V0 minus will be equal to V0 plus equal to V0, and where the V0 minus can be defined as the voltage across the capacitor just before the switching, and V0 plus will be defined as a capacitor voltage immediately after the switching. And in this circuit we can just have a typically a step response we can define of this RC circuit. I mean, when it is just like you are going to close with the unit response function. So, it is like a circuit like you can see dV by dt, because voltage across the capacitor can be defined as a variable V, that is C dV by dt, plus V minus, because the typically current through the, you can call it across through the, you can call resistance will be mu minus Vs ut divided by R. So, this will be the like equation of this circuit, current flowing into this total circuit, or you on the node also you can say that what will the. So, this can be further expressed as dV upon dt plus V upon RC equal to Vs ut upon RC, and where V is the voltage across the capacitor for t greater than 0. The circuit becomes in this manner, and this will become a function like dV upon dt for t greater than 0, means that your ut has become 1. So, it becomes dV upon dt plus V upon RC equal to Vs upon RC, and then from which we can define dV upon dt equal to minus V minus Vs upon RC, or we can keep it like a dV upon V minus Vs equal to dt upon RC, which of course, we can take a integration. So, we can find out the response of this in terms of that will become ln V minus Vs, of course, from Vs to Vt, or equal to minus t upon RC from 0 to t, and it can be defined as logarithmic Vt minus Vs minus log V0 minus Vs equal to minus t upon RC plus 0, or it can be finally expressed as a one function log, or ln V minus natural log V minus Vs upon V0 minus Vx equal to minus t upon RC, taking exponential on both the sides. So, you can just represent it as a V minus Vs upon V0 minus Vs equal to e to power minus t upon tau, or where the tau is your RC, and Vt equal to Vs plus your V0 minus Vs e to power minus t upon tau for t greater than 0. This is typically the kind of the response. I mean, you can call it the how the capacitor voltage, I mean voltage across the capacitor will be changing with respect to the time for t greater than 0, like. And of course, in your lamp that is really the response is. So, Vt equal to, we can define equal to V0 if t is less than 0, and for t greater than 0, of course, it will change because of the close of the switch, it will be Vs plus V0 minus Vs e to power minus t upon tau, and that typically you can call it how the voltage varies with respect to time across the capacitor. And the complete response or the total response of the RC circuit to a sudden application of DC source, assuming the capacitor is initially charged to a given value like V0, how the voltage of the capacitor goes to from V0 to Vs, and this response is of RC circuit with initially charged capacitor of to V0. Assuming that the capacitor is in charge initially, then V0 will be equal to 0 and Vt will be equal to 0 if t is less than 0, and it will be Vs 1 minus t e to power minus t upon tau for t greater than 0, or you can just express here Vt will be equal to Vs 1 minus e to power t upon tau into ut as a step response function. In terms of step response function, the response of the circuit when capacitor is completely discharged, like. So, this is the complete step response of the RC circuit when the capacitor is initially in charge, and the circuit through the capacitor is obtained as I t equal to C dV by dt, and that can be C upon tau Vs e to power minus t upon tau, and where tau is RC for greater than t greater than 0, and this I t will be equal to Vs upon R e to power minus t upon tau ut as a typically a current flowing through the circuit like after t greater than 0, like. and it can be finally explained I t equal to V s upon R t e to power t minus tau into u t. And this is how the response look like. For the here the V t changes from your 0 to, because capacitor was uncharged, so it start the voltage from 0, it go to V s, and the current going to this circuit start from V s upon R. The capacitor behave initially like a short circuit, so current is decided by only resistance initially, and then when the capacitor start charging, then the current start reducing, and finally it goes to 0 when capacitor charges to full value of the V s. So, this is step response of RC circuit with initially in charge capacitor, and say left side is the your voltage response, right is the current response of the circuit like. Well, it is evident that the V t has a two component, the classical two ways of decomposing this into two component. The first is to break it into a natural response and a force response, and the second is to break into a tangent response and steady state response. That is how we really define. So, complete response will be equal to natural response, that is corresponding to stored energy, and plus force response by the independent source, and that will be equal to V equal to V n plus V f, and this V n is equal to V 0 e to power t minus tau, and V f equal to V s 1 minus e to power t minus tau. So, that is how you can call it complete response of the your RC circuit, consisting of natural response plus your force function response together. Now, coming to with the similar example with the RL circuit, the step response of an RL circuit is of the similar circuit like we have a independent voltage source V s, and we have a switch followed by the inductor, and current I in the circuit response when we we represent this circuit as a step response V s u t, and R because the switch is closed, so it is R, and we have a current flowing through the inductor. So, it is a RL circuit with the step input voltage as we just saw as a your step response input like. So, for the analyzing it, the response is the sum of the tangent response and the steady state response, and I equal to I t plus I s s, and tangent response is always a decaying exponential function, because we call it like a natural response, that will be I t equal to a e to power minus t upon tau, and where the tau is your L upon R time constant for this RL circuit. So, steady state response is the value of the current a long time after the switch is closed, and the transient response only die out after approximately 5 time constant. We have seen that after 5 time constant it will be only around 1% typically of the final. At that time the inductor becomes a short circuit and the voltage across it is 0, and mainly the current decided by the resistance of the circuit like total resistance of the circuit. The entire source voltage appears across the resistance R, and thus the steady state response is I s is equal to V s upon R, because that resistance decide the resistance of the circuit decide the final current, and your total response becomes I equal to a e to power minus t upon tau plus V s upon R. And we can determine this constant A from the initial value of I mean as you can see the circuit initially and after closing, after applying the unitary response function. So, let the I 0 the initial current flowing through the inductor, and I 0 plus is equal to I 0 minus, that is I 0, and at time t equal to we can call it I 0 is A plus V s upon R, and then A becomes I 0 minus V s upon R, and on substitution to that equation typically of this A value equal to I 0 minus V s upon R, and I t will become V s upon R plus I 0 minus V s upon R to power e tau minus t, and this is the complete response of the RL circuit, what we discussed in the similar manner as we discussed earlier for RC circuit. So, this is the complete response of RL circuit, and we can say I t equal to I infinity plus I 0 minus I infinity e to power t e to power minus t upon tau, where I 0 and I infinity are the initial and final values of I respectively in this circuit like. So, if the switching take place at time equal to t 0 instead of t, so I t will be equal to I infinity plus I t 0 minus I infinity and e to power e minus t 0 divided by tau, and if I 0 equal to 0, then it becomes I t equal to 0 for t less than 0, and it becomes V s upon r 1 minus e to power minus t upon tau for the greater than t equal to 0, where I t equal to V s upon r 1 minus e to power tau minus upon t upon tau into u t. That becomes typically the response. So, this is the step response of RL circuit with no initial inductor current, and voltage across the inductor is obtained as V t equal to L di by dt or equal to V s upon tau L upon r e to power minus t upon tau, where tau equal to L upon r for t greater than 0. So, we get here the response typically, current response will be starting from 0 and final current will be going to V s upon r, and for voltage response it start from typically V s and it goes to 0 across the inductor, and the function is defined as your V t equal to V s into t e to power minus t upon tau into u t. Well, these are the typical response of this first order 2 system, RC circuit and RL circuit with the step response. Similarly, you can define the response with the impulse function as well as to ramp function if you really need. We have some sort numerical problem based on this concept. So, starting with the first problem, the switch given here in the figure has been a position A for a long time. At t equal to 0, the switch move to B and determine the V t, typically the voltage across the capacitor for t greater than 0, and calculate the value at t equal to 1 and 4. So, you can call it initially the the capacitor is connected to the circuit source of your 24 volt through the resistance, and at t equal to 0 it is close to the typically of terminal B, and you can call it in the capacitor, charge capacitor goes to the second circuit, and still the voltage across the capacitor and the source of 30 volt will be different. So, certainly there will be some response to go further finally to steady state Interesting problem. So, for t less than 0, the switch is at position A and capacitor acts like an open circuit to DC, but V is the same as the voltage across the 5 kilo ohm resistor. Hence, the voltage across the capacitor before t equal to 0 is obtained by voltage division, that is V 0 minus equal to 5 upon 5 plus 3 into 24, that is a 15 volt across the capacitor, of course, t less than 0, and now the capacitor voltage cannot change instantaneously. So, we call it V 0 equal to V 0 minus equal to V 0 plus equal to 15. For t greater than 0, the switch is in position B. Now, Thevenin circuit, Thevenin resistance connected to the capacitor RTH is 4 kilo ohm, and the time constant is now tau equal to RTH into C, that is 4 into 10 to power 3, that is 4 kilo ohm into 0.5 into 10 power minus 3, that is equal to 2 seconds, and where V infinity is 30 volt, capacitor acts like a open circuit to DC at a steady state from the source of 30 volt. Now, it will be going from 30 volt to typically from that 15 volt to 30 volt. So, V t will be equal to V infinity plus V 0 minus V infinity e to power minus t upon tau, and that value we should put that V infinity is 30 volt plus V 0 is 15 volt minus finally V infinity 30 volt. So, 15 minus 30 e to power tau minus t by 2, and that is 30 minus 15 e to power minus 0.5 t volt. At t equal to 1, the voltage will be equal to V 1, that is for 1 second, and 30 minus e to power 30 minus 15 e to power minus 0.5, that is 20.9 volt, and at t equal to 4, V at V 4 second will be 30 minus 15 e to power minus 2 into that will be equal to 27.97 volt, and that is how we define the response. Finally, it will be going for very large time. You have seen for 1 second it was going from 15 volt, it has gone after 1 second to 20.9 volt, then after 4 second it has gone 27.97 volt. Now, coming to an example second, problem 2 in figure, the switch has been closed for long time and it is open at t equal to 0, find the I and V for all the times. So, here is we have a switch which have been closed and now we want to open it. It means when switch is closed, you can just see, you can find out what is the typically the voltage goes from which value to which value in this corresponding to step function. Means this switch is operated from this step function virtually, because this will be energizing the circuit after opening the switch So, the note the resistor current I can be discontinuous at t equal to 0, while the capacitor voltage V cannot be hence it is always better to find the V and then obtain I from V. So, by now you can see the both the circuit, when circuit is let us say the close and the open, I mean how the circuit changes from one circuit to the second circuit like. So, by the definition of U step function we can define 30 u t equal to 0 for t equal to less than 0 and t equal to less than 0 and 30 for t greater than 0. So, from this t less than 0 we can find out the V is your 10 volt, because that 10 volt was directly applied across it, and I is typically you can call it here minus V upon 10, and that will be minus 1 ampere, because the voltage difference was typically found. So, the capacitor voltage cannot change instantaneously, and V 0 will be equal to V minus equal to 10 volt, that is from the capacitor. Now, for t greater than 0 the switch is open and the 10 volt voltage source is disconnected from the circuit, and the 30 ut voltage source is now operative. So, circuit becomes as shown here typical, and V infinity is obtained by using the voltage division typically in this circuit. So, it becomes V infinity equal to 20 divided by 20 plus 10, the voltage across capacitor is correspond to like your 20 ohm, and that will be 20 divided by 20 plus 30 divided into 30, that is 20 volt. So, it goes from 10 volt to 20 volt from, you can call it from your T 0 to going to T infinity like. So, Thevenin resistance at the capacitor terminal can be defined as parallel resistance of 10 or 20 ohm, that is a 20 by 3 ohm, and time constant is given like your typically as a RC T equal to RTH RC, that 20 by 3 into 1 by 4, that is 5 by 3 second, and now you can define V t equal to V infinity plus V 0 minus V infinity e to power t upon tau, or that will be equal to 20 plus 10 minus 20 e to power minus 3 upon 5 t, and that will be equal to 20 minus 10 to power e 0.6 t into 0.6 t volts like. And I is the sum of the current flowing through the 20 ohm resistor and the capacitor. So, I will be equal to V upon 20 plus C dV upon dt, and that will be equal to like you can say 1 minus 0.5 into power minus 0.6 t plus 0.25 into minus 0.6 into minus 10 e to power 0.5 minus 0.6 t, and that becomes equal to 1 plus e to power minus 0.6 t, from which you can say it is a V plus tan I equal to 30, and that now you can define the voltage as a 10 volt for t less than 0, and for t greater than 0 it will be 20 minus 10 to power minus 0.6 t volts, and current will be minus 1 ampere. This was initially for long period for t less than 0, and it will be 1 plus e to power minus 0.6 t for t greater than 0. So, that is about the problem 2. Now, coming to the problem 3, find the IT for the circuit shown here in figure for t greater than 0. Assume that the switch has been closed for longer time. So, this circuit was closed for longer time, and typically you can call it the current in the inductor of course was flowing under steady state, and the drop across the inductor will be 0, but we insert the resistance, so current certainly have to decrease from that value to higher value. Let us discuss the solution. So, when t less than 0, the 3 ohm resistor is short circuited and the inductor acts like a short circuit. The current through the inductor at t minus 1 is just before the t equal to 0 is I 0 minus, that is 10 upon 2 equal to 5 ampere, and then the inductor current cannot change instantaneously. So, I 0 will be equal to I plus I theta plus I 0 plus equal to I 0 minus equal to 5 ampere, and for t greater than 0 the switch is open. Now, the 2 ohm and 3 ohms resistors are in series. So, you can call it I infinity will be now 10 divided by 2 plus 3. So, this will be now 2 ampere. So, I infinity will be 2 ampere, I 0 is your 5 ampere. So, current have to go from 5 ampere to 2 ampere after opening the switch. So, the Thevenin resistance across the inductor terminal is RTH equal to 2 plus 3 now equal to 5 ohm, and now for the time constant t equal to L upon RTH will be 1 upon 3, that is the inductance divided by 5 equal will be 1 upon 15 second, and you can say I t will be equal to I infinity plus I minus I 0 minus I infinity into e to power minus t upon tau. So, that will be equal to 2 plus in bracket 5 minus 2 e to power minus 15 t, that will be 2 plus 3 e to power minus 15 t for t greater than 0. So, coming to the problem 4, at t equal to 0, the switch 1 in figure 1 is closed and the switch 2 is closed at 4 seconds later. Find I t for t greater than 0 and calculate if I for t 2 seconds and I for and t 5 seconds. So, this is closed at 0 second, this closed at 4 seconds, and we have to find out, typically you can call it I t, the current through inductor at different time period of 2 seconds and 5 seconds, means after first tangent and second tangent. So, now coming to the solution of it, consists of 3 time intervals t less than 0, t 0 to 4 second and t greater than 4 second separately, and for t less than second switch S1 and S2 are open. So, that I equal to 0. So, the inductor current cannot change instantaneously. So, I 0 will be equal to I 0 plus equal to I 0 minus equal to 0 ampere, and now for t 0 to 4 second S1 is closed, I mean this switch is closed. So, the 4 ohm and 6 ohm resistors are in series. So, you can have a typically the I infinity current corresponding to that 40 plus 4 plus 6 second, that is 4 ampere, and RTH will be sum of these two resistance 4 plus 6 10 m, and tau will be your L upon RTH equal to 5 upon 10, that is a half second. And now you can have a like typically the solution from first part, I t equal to I infinity plus I 0 minus I infinity e to power t upon tau, and that will be equal to 4 plus 0 minus 4 e to power minus 2 t, and that will be 1 minus e to power 2 t ampere for 0 to 4 second. So, at t greater than 4 second S2 is closed. So, 10 ampere 10 volt source is now connected and the circuit changes. The initial current is your I 4 equal to I 4 minus equal to 4 e to power 1 minus e to minus 8 equal to 4 ampere. And now, when both the switches are closed, so to find out I infinity, let the V with the voltage at node P using Kirchhoff's current law at node P, that is virtually the current coming from this side. So, 40 minus V, typically 40 minus V divided by 4, that will be the current coming from this side, plus your current typically coming from 10 volt, 10 minus V upon 2, it will be equal to your V itself going to be by 6 in final one, and that will give you V equal to 180 upon 11, and I infinity will be by V by 6, I mean that current itself. So, it will be like 30 by 11. So, it will be 2.72 ampere current in finally in the inductor, and Thevenin resistance at the inductor terminal is RTH equal to the 4 ohm into 2 in parallel plus 6 ohm, that become 22 by 3 ohm. So, IT will be equal to I infinity in bracket I 4 minus I infinity e to power minus t upon t minus 4 by tau, and for t greater than 4 second, and we need t minus 4 in the exponential necessary of time delay. So, I t will be equal to 2.727, putting the value of that I infinity plus in bracket 4 minus 2.2727 e to power minus 4 t minus 4 divided by tau, and where tau is your 15 by 2, and putting the value here 2 minus 727 plus 1.273 e to power minus 1.4667 t minus 4 for t greater than 4, and this whether t equal tau equal to L upon RTH, that is 5 upon 22 by 3, that becomes your 15 by 22 second. And putting together IT will be equal to 0 for t less than 0, IT will be 4 into 1 minus e to power minus 2 t for t get 0 to 4 second, and it will be 2.77727 plus 1.273 e to power minus 1.4667 t minus 4 for t greater than 4. So, at time t equal to 2, I mean it will be I 2 will be 4 1 minus e to power minus 4, that will be equal to 3.93 ampere, and at t equal to 5 I 5, that will be for the last equation. From the last equation will be 2.7327 plus 1.273 e to power minus 1.4667 equal to 3.02 ampere. Now, coming to problem 5, for the network shown here, find the Vt for t greater than 0. I mean the Vt is the voltage typically across this inductor. Now, coming to typically t greater than 0 means that typically switches get open like. So, for the you can say for the t less than 0 the switch is closed for long time and inductor will behave like a short circuit, and applying the Kirchhoff's current law at the node V 1 here, because it will be having current from typically from all 5 branches. So, V 1 by 12 that is corresponding to current here, V 1 by 20 current flowing through here, V 1 by 6 current from here, and current typically from your this side V minus 20 by 5, that will be equal to 2 ampere current source, and from which you can get V 1 equal to 12 volt. Now, here hence the current through the inductor at t equal to t 0 plus will be I 0 equal to V 1 by 6, that is 2 ampere. When the switch is open, resulting the circuit can be converted into Thevenin equivalent circuit with the inductor across the load terminal. So, Thevenin of this can be equated similar to typically of this, because voltage source can be removed short circuited there. So, you can find out Thevenin equivalent of this for RTH calculation. So, RTH is 5 in parallel with the 20 plus 6, that is 10 ohm, and time constant will be RTH equal to 0.5 divided by 10, that is 0.05 second, and inductor current for the first order circuit is given I t equal to I infinity plus bracket I 0 minus I infinity e to power minus tau upon t upon tau, and I infinity where I infinity is 20 upon 6 in parallel 20 plus 5 into 20 upon 20 plus 5, that is 1.6 ampere. Like. Hence, I t will be equal to 1.6 in bracket 2 minus 1.6 e to power minus t upon 0.005, and that will be equal to 1.6 plus 0.4 e to power minus 20 t, and V t will be equal to L d by dt, that will be equal to 0.5 minus into minus 20 into 0.4 into power minus 20 t, that will be equal to minus 4 into e to power minus 20 t volt, because the typically with the time this inductance voltage drop will go on reducing. For infinity time it will become 0. So, inductor cannot store typically finally any voltage across it under steady state. So, these are the typical some of the practice problem which you can solve it on the same way as we discuss typically the problem in the earlier like. And well, yeah, these are the some of the problem which you can solve yourself like. And there are some quick questions unsolved. So, you can say if the switch is closed at t, what is the current in the figure of this circuit. So, I mean you can just see here the current will be typically like a 10 ampere. Similarly, you can solve for this. So, it will be 0.5. So, these are the typical very short quiz questions you can probably do it like, and these are the references. Thank you.